Have you ever wondered why the east coast of South America fits almost perfectly into the west coast of Africa? Is it just a coincidence, or is there a logical explanation behind it? This intriguing question peeks into the heart of one of the most fascinating geological studies, the concept of continental drift. It's a journey of discovery that takes us millions of years back in time, revealing the dynamic nature of our planet. Well, the answer lies in the remarkable theory of continental drift and the story of our ever-changing planet. Enter Alfred Wegener, a German meteorologist who dared to challenge conventional wisdom in 1912. In a time when the scientific community accepted the continents as immovable fixtures, Wegener, a man more accustomed to studying the weather than the Earth, proposed a bold and controversial theory. He suggested that our continents are not stationary, but rather, they're in a slow, constant motion. This hypothesis, which we now know as the continental drift theory, was a groundbreaking perspective in the early 20th century. Born in Berlin in the late 19th century, Wegener was a curious mind, always eager to uncover the truths of the natural world. His interest in meteorology led him to polar expeditions, where he observed geological phenomena that didn't quite align with the accepted theories of his time. In 1912, Wegener proposed his audacious hypothesis, suggesting that the continents were once a single landmass, a supercontinent he named Pangaea. Over time, he said, this supercontinent broke apart, and the fragments drifted to their current positions. It was a bold idea, one that dared to challenge the status quo. But the scientific community was not ready to embrace such a radical departure from established beliefs. Wegener faced a tidal wave of skepticism and criticism. His peers questioned his credentials, dismissing his theory as imaginative speculation, lacking concrete evidence. They argued, how could a meteorologist possibly understand the complex mechanisms of the Earth's crust? But Wegener was undeterred. He spent the rest of his life gathering evidence to support his theory, collecting data about fossils, rock formations, and climate patterns across continents. Even though he passed away before he could see his theory widely accepted, his relentless pursuit of truth laid the groundwork for a seismic shift in geoscience. Wegener may have been dismissed during his time, but his theory would later revolutionize our understanding of the Earth. In the face of adversity, Wegener stood firm, his bold hypothesis proving to be a trailblazing contribution to the field of geology. His story is a testament to the power of curiosity and the courage to challenge established norms. Wegener wasn't just making wild guesses. He had substantial evidence to back up his claims. Now, let's dive into the treasure trove of evidence he unearthed, starting with fossils. Imagine finding the same fossil species in places as disparate as Africa and South America. That's exactly what happened with the fern-like plant Glossopteris and the reptile Mesosaurus. These organisms were not Michael Phelps. They couldn't swim vast oceans. Their fossil presence across separate continents was a cryptic hint at a past where these landmasses were once neighbors. Moving on to rocks, and no, we're not starting a band here, rock formations across different continents showed striking similarities. The Appalachian Mountains in North America, for instance, share a family resemblance with Scotland's Highlands. These matching geological features suggested that these regions were once part of the same landmass. Now let's talk about the weather, or rather the climate. Evidence of ancient glaciations in today's tropical regions like Africa and India seemed out of place. How could sheets of ice cover these warm regions? The answer lay in their past location. They were once situated near the South Pole as part of Pangaea. Then there were the coal deposits found in Antarctica. Coal forms from plant matter in warm, swampy conditions. Antarctica today is anything but warm and swampy, but it wasn't always this way. When it was part of Pangaea, it enjoyed a much toastier climate. Wegener's evidence, though met with skepticism, painted a compelling picture. Fossils, rocks, and ancient climate clues pointed towards a dynamic Earth where continents drift and dance over geologic timescales. They told tales of a time when our scattered continents were once a familial cluster, a supercontinent known as Pangaea. Each piece of evidence was a puzzle piece, slowly revealing the picture of a once united supercontinent, Pangaea. But how do continents move? What forces are powerful enough to shift entire landmasses? The answer lies in a remarkable geological concept: plate tectonics. To put it simply, the Earth's outer shell isn't a single piece but is composed of large slabs of rock called tectonic plates. These plates fit together like a gigantic puzzle covering the Earth's surface. Now these plates aren't stationary. They're constantly moving, albeit at a snail's pace. Imagine your fingernails growing, that's about the speed we're talking about. So why do these plates move? It's all about heat. The Earth's core is like a huge furnace generating immense heat. This heat creates convection currents in the underlying semi-fluid layer called the mantle. As the hot magma rises, it pushes the tectonic plates above, causing them to move. When it cools and sinks back down, it pulls the plates along, creating a cycle of movement that never stops. This brings us to another fascinating concept: seafloor spreading. Picture this. At the bottom of the ocean, there are massive underwater mountain ranges called mid-ocean ridges. Here, magma from the Earth's mantle rises to the surface, creating new seafloor. As the magma cools and solidifies, it pushes the existing seafloor away. This process, over millions of years, moves the continents apart. But what happens when these moving plates meet? Well, that's where things get really interesting. They can either slide past each other, creating faults, move towards each other, forming mountains and volcanoes, or one can slide under the other, a process known as subduction, causing deep-sea trenches and triggering earthquakes. These mechanisms of plate tectonics and seafloor spreading are the invisible forces that have sculpted our planet's surface over billions of years. They're the reason why we have continents and oceans, mountains and valleys, and why our planet looks the way it does today. These processes are not only responsible for the drift of continents, but also for the creation and destruction of Earth's physical features. The movement of continents doesn't just reshape our planet's surface, it sparks a domino effect, influencing everything from climate to biodiversity. So let's talk about the aftermath of this grand geological shuffle, the continental drift. Picture a deck of cards. As you shuffle, you're essentially mimicking the process of plate tectonics. Some cards, or in this case land masses, collide to form mountain ranges. The Himalayas, Andes, and the Alps, all products of this tectonic card game. But there's more. As continents drift, they carry with them their climates, often dramatically altering weather patterns. The Sahara Desert, for instance, wasn't always a hot, sandy expanse. Millions of years ago, when it was closer to the equator, it was a lush green landscape. Now let's not forget about our planet's diverse array of flora and fauna. Ever wondered why you find similar species on different continents? Well, it's all thanks to continental drift. As landmasses move, they transport their resident species, leading to a global mix and match of biodiversity. This process also played a significant role in evolution. Isolation of continents led to species adapting to their new environments, resulting in the breathtaking variety of life we see today. So, from the towering mountain ranges to the shifting climates, from the distribution of species to the evolution of life, every aspect of our world is touched by the seemingly slow, but incredibly powerful process of continental drift. Indeed, the drift of continents has played a significant role in shaping the world as we know it. Despite initial resistance, Wegener's theory has stood the test of time thanks to modern technological advances. Today we have a wealth of cutting-edge tools and techniques that offer us a lens into the very heart of our planet, providing compelling evidence to support the theory of plate tectonics. Let's start with GPS measurements. Now, GPS isn't just for finding the nearest coffee shop when you're lost in a new city. It's also a powerful tool in geology. By placing GPS receivers on different continents, scientists can measure the precise movements of these landmasses. These measurements reveal that continents are indeed drifting, albeit at a snail's pace. In fact, most continents drift at a rate of 1 to 4 inches per year. That's about as fast as your fingernails grow. Next, we have paleomagnetic data. This refers to the study of the record of the Earth's magnetic field in rocks. When lava cools and solidifies into rock, tiny magnetic minerals within align themselves with the Earth's magnetic field, acting like a compass needle frozen in time. By studying the orientation of these minerals in rocks of different ages across the globe, scientists can track the historical movement of the continents. Lastly, let's talk about seismic activity. Earthquakes and volcanic eruptions are dramatic evidence of the ongoing tectonic activity beneath our feet. These events occur mainly along plate boundaries where the Earth's crust is being created, destroyed, or deformed. By studying the locations and patterns of seismic activity, scientists can map the edges of tectonic plates and monitor their movements. So, there you have it. From the humble GPS in your car to the study of ancient rocks and the monitoring of Earth's rumblings, modern technology has provided a trove of evidence supporting the theory of continental drift. The continents continue to drift, and while we may not feel it, we now have the tools to measure it, confirming once and for all Wegener's groundbreaking theory.